DAC techniques. Mainly we are having two types of basic DAC techniques. They are binary weighted resistor DAC technique and R by 2R ladder type DAC techniques. Coming to this case, in these two techniques, the shunt resistors are used to generate n binary weighted currents, and these binary weighted currents are controlled by using the binary input data and then converted into analog equivalent voltage for the given digital input data. Such type of digital to analog converters are called as current driven digital to analog converters. Now first I am going to discuss about binary weighted resistor technique. Here we are going to be used the shunt resistors. N shunt resistors are used, okay, depending upon the number of bits, that is depending upon the input bits, we are going to be consider the number of shunt resistors, and in this case the shunt resistors are used to generate n binary weighted currents, and these n binary weighted currents are controlled by using the digital inputs which we are applied at B1, B2, B3 so on up to Bn, and this binary weighted resistor DAC technique consists of a op-amp which is having high input impedance. That's why the total current passing through the feedback resistance RF, okay, and the total current IT will be equal to I1 plus I2 plus I3 plus so on up to In. Now whenever the binary input is equal to 1, then what happened, and whenever the binary input is equal to 0, then what happened? We have to know these two conditions, okay. So first, whenever the binary input is equal to 1, then immediately the switch will be closed and the resistance is connected to the reference voltage VR. Whenever the binary input is 0, then the switch is open and it leaves the resistor as open, and now whenever the switch is closed, then the current produced is calculated as I is equal to VR divided by R whenever the switch is closed. So whenever the switch is open, then what happened to the current? Then the current I is equal to 0, and now if the binary input is taken as 1, all the binary inputs are taken as 1, then what happened? All the switches are closed. Then the total current produced is calculated by using the formula IT is equal to I1 plus I2 plus so on plus In. Here if you observe in the circuit diagram, here we are using the identical reference voltage VR and we are using the scaling resistors, okay, that is for the first one we are having the resistance value is 2R, and the second one we are having 4R so on up to the last one we are having for 2 power n into R. That means we are using the scaling resistors in this case, and the reference voltage is same for all the resistors, which is nothing but VR. So IT is equal to I1 plus I2 plus so on plus In, and these currents are controlled by using the binary input data. So whenever the switch is binary input is equal to 1, then the switch is closed, then we will generated the current up corresponding to that switch position, okay. Now the current IT is passing through the feedback resistance RF. Why? Because here the op-amp is having the high input impedance, and the output voltage V0 is equal to minus IT into RF, okay, where IT is nothing but I1 plus I2 plus so on up to In. So V0 is equal to minus of I1 plus I2 plus I3 plus so on plus In into RF. And what about I1, I2, I3, so on up to IN? Here I am taking I1 is equal to B1 into VR divided by 2R, and I2 will be equal to B2 into VR divided by 4R, and I3 is equal to B3 into VR divided by 8R, so on. IN is equal to Bn into VR divided by 2 power n into R. Substitute those current values in this expression, then we will get V0 is equal to minus of B1 into VR divided by 2R plus B2 into VR divided by 4R plus so on plus Bn into VR divided by 2 power n into R into RF. So take common as VR by R. So what happened? Minus VR by R into RF. So B1 into 2 to the power of minus 1 plus B2 into 2 to the power of minus 2 plus so on plus Bn into 2 to the power of minus n. So if we have chosen RF is equal to R, then what about the output voltage? V0 will be equal to RF and R will be cancelled. Why? Because here we are choosing RF is equal to R. So we will get it as V0 is equal to minus VR into B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus so on plus Bn into 2 to the power of minus 1, which is nothing but the analog output voltage for the given binary input data. Once again I am telling you the principle behind this binary weighted resistor technique is here the shunt resistors are used to generate n binary weighted currents, and these currents are controlled by using the binary input data, okay, and then converted into output voltage, which is nothing but the analog output voltage for the given input digital data, okay, which is nothing but the basic principle behind the binary weighted resistor DAC technique. And now we are moving on to the disadvantages of this binary weighted resistor DAC technique. What are the main disadvantages in this binary weighted resistor DAC technique? We are having mainly 3 disadvantages in this technique. What are they? First one is wide range of resistors are required for the construction of binary weighted resistors. Suppose if you are taking 8 input datas, that is 8 binary input datas if you have chosen, then you require 8 resistors, and the resistors are from 2R to 4R, 8R, so on up to 2 to the power of 8 into R. That means the smaller resistor is 128 times lesser than the larger resistor. Okay, this is the main disadvantage in the binary weighted resistor DAC technique. And the second one is, because of these wide range of resistors, there is a limit for the larger value of the resistor as well as the smaller value of the resistors, and it is impracticable to fabricate the large value of the resistor on IC, and the voltage drop across the large value of the resistor because of the bias current changes the accuracy of the system also. The finite resistance of switches disturbed the binary weighted relationship among various currents, particularly in the most significant bit position where the current settling resistance value is very small. These are the 3 basic disadvantages which we are observed in this binary weighted resistor technique. To avoid these disadvantages, we are going for the second one, which is nothing but the R by 2R ladder DAC technique. R by 2R ladder type DAC technique technique. In this case, we are having two types. One is current streaming mode and the other one is voltage switching mode. So first I am going to explain the current streaming mode, which is also called as inverted R by 2R ladder type DAC technique. If you observe the circuit diagram with the previous DAC technique, which is nothing but the binary weighted resistor DAC technique, there we are using n number of resistors, but in this case we are using only two resistors. One is R and the other one is 2R. There we are follow the voltage is constant, that is the reference voltage is constant and the resistors are scaling. If you observe the circuit diagram, here the resistances are identical and the voltage is scaling at the nodes. So at the first node we are having VR by 1, which is nothing but VR by 2 to the power of 0, and at the second node which is nothing but VR by 2 to the power of 1. At the third node we are having VR by 2 to the power of 2. Like that we are getting at the last node, we are getting it as VR divided by 2 to the power of n minus 1. So here we are considering the voltage scaling. Now coming to this case, here also we are using the shunt resistor to generate n binary weighted currents, and these currents are controlled by using the binary input data with the help of switches. Okay, whenever the binary input data is equal to 1, then it connects the corresponding switch to the inverting input terminal of an op-amp. So what we can conclude is, depending upon the binary input value, the switches will be connected to the ground or it may be connected to the inverting input terminal of an op-amp. And if you observe the circuit diagram, the non-inverting input terminal of an op-amp is connected to ground. According to the virtual ground concept, the potential at the inverting input terminal of an op-amp is also at ground potential. So both the switch positions are at the same potential. So whatever may be the binary input you applied at the binary input data you applied at the switches, we generated the constant current. So I1 will be equal to VR by 1 divided by 2R, and I2 will be equal to VR by 2 divided by 2R, and I3 will be equal to VR by 4 divided by 2R. So this we can be rewrite as I1 divided by 2, and this we can be rewrite as I1 divided by 4. Like that we can rewrite as IN will be written as VR divided by 2 power n minus 1 divided by 2R. So we can rewrite it as I1 divided by 2 power n minus 1. And one more thing you have to observe in this inverted R by 2R ladder type DAC technique is, for generating the voltage scaling require a series resistance to generate the voltage drop across the two nodes. That's why here we are connecting a resistance R between the two nodes. For generating the voltage scaling at the nodes, we are using the resistance R. And one more thing you have to remember in this inverted R by 2R ladder type technique, whatever may be the binary input you have chosen for the input values, that means whether it may be 1 or whether it may be 0, the node voltages are always constant. That means at the first node we are having VR by 1, and the second node we are having VR by 2, so on. At the last node we are having VR by 2 to the power of n minus 1 into R. Node voltages are same irrespective of the input voltages which we are applied at the input terminal. Because of this, which avoids the stray capacitance effect, total current IT is calculated as I1 plus I2 plus I3 plus so on plus IN. According to the binary input values, we are going to get the corresponding input current, whether it may be I1, I2 or I3, so on up to IN. If the binary input B1 is equal to 1, then we are getting the current as I1 is equal to VR by 1 divided by 2R, and if the binary input at B2 is equal to 1, then we are going to get VR by 2 divided by 2R. Like that, if the switch positions are closing, whenever the binary input is 1, then only where the appropriate current will be flowing across the resistance RF. We are going to be used the summing amplifier, which is having the high input impedance. So the total current passing through the op amp is same. So IT will be passing across the resistance RF. So we will get it as V0 will be equal to minus IT into RF. So from this, what we can write it as minus of I1 plus I2 plus so on plus IN into RF. So which will be equal to minus of B1 into VR divided by 2R plus B2 into VR divided by 4R plus so on plus Bn into VR divided by 2 power n into R into RF. Why? Because VR by 1 by 2R is nothing but VR by R. VR by 2 by 2R is nothing but VR by 4R. Like that, I am directly representing as last one Bn into VR divided by 2 power n into R. Okay. So take common as VR by R. So we will get it as minus VR by R into RF into B1 into 2 to the power of minus 1 plus B2 into 2 to the power of minus 2 plus so on plus Bn into 2 to the power of minus n. So we are getting finally output voltage V0 is equal to minus of VR into. Why? Because if we are choosing RF is equal to R, then both will be cancelled. Then we will be get it as minus VR into B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus so on plus Bn into 2 power minus n, which is nothing but the analog equivalent voltage for the given digital input data. Main advantages of this inverted R by 2R ladder type technique is, first one is here we are using only two resistance. Yes or no? One is 2R and the other one is R. Whenever the bits are increasing, then we can just adding another 2R and R resistor network, then we can increase the circuit to n number of bits also. And because of the voltage scaling between the nodes, we are reducing the effect of stray capacitance. Coming to the IC1408 DAC, which is nothing but an 8-bit R by 2R ladder type DAC technique, which consists of 8 inputs and which is used to design where the output current is linear product of binary input word. For that we are going to be used the IC1408. Here I am showing you the pin diagram as well as block diagram of IC1408. Here which consists of 16 pins, and the first pin is nothing but the output range control. So the range of the output is decided by using this first pin, and the second pin is nothing but ground. For any IC required the ground pin, and the third pin is VEE, and the fourth pin is nothing but the output current. In this case IC1408 we are going to produce the output current, and that output current will be converted to voltage by using the current to voltage converter. And next all these are the switches A1, A2, A3, A4, A5, A6, A7 and A8 are nothing but 8 high speed current switches and which requires 2 reference voltages for IC1408 and it requires 2 power supply voltages. One is plus VCC and the other one is minus VEE. VCC range is plus 5 volts and the VEE range is from minus 5 volts to minus 15 volts, and the compensation resistor is used to reduce the bias current in that IC1408. And now coming to the block diagram of IC1408. IC1408 consists of reference current amplifier and R/2R ladder and 8 high speed current switches, and switches are controlled by using the binary input data which we are applied at the 8 input terminals of an IC. So the current switches are controlled by using the binary input data. IC1408 is an 8-bit DAC ladder R/2R technique and which is compatible with TTL and CMOS logic and which requires 2 milliamperes of reference current for the full scale input, and the supply voltages are VCC is equal to plus 5 volts and VE is equal to minus 5 volts to minus 15 volts. And coming to the reference current, how we are going to generate the reference current is with the help of reference voltage and R14 resistance we are going to generate the reference current. The total reference current is derived with the help of reference voltage and R14 resistor, and always R14 resistor will be equal to the R15 resistance to match the high input impedance of the current amplifier. Figure shows the typical circuit diagram of IC1408. The output current I0 can be calculated by using the formula I0 is equal to V reference divided by R14 into A1 divided by 2 to the power of 1 plus A2 divided by 2 square plus A3 divided by 2 cube plus A4 divided by 2 to the power of 4 plus so on plus A6 divided by 2 to the power of 6 and then plus A7 divided by 2 to the power of 7 and then plus A8 divided by 2 to the power of 8. And the binary input A1 through A8 can be any value. That means it may be 1 or 0. For the full scale input values, the output current is calculated as I0 is equal to V reference divided by R14, where R14 is equal to 2.5 kilo ohms and V reference is equal to plus 5 volts, and for the full scale input voltage A1 to A8 will be equal to 1. So 1 by 2 plus 1 by 4 plus 1 by 8 plus so on plus 1 by 2 to the power of 8. So we will get the output current as 1.998 milliamperes. Compare the output current with the input reference current. The output current is slightly less than the input reference current, which is nothing but 2 milliamperes. Input reference current will be equal to 2 milliamperes, and the output current can be converted into voltage with the help of current to voltage converter, and the output voltage is calculated as V0 is equal to I0 into R, okay, which is nothing but 1.998 into 2.5, which is nothing but 4.98 volts, where resistance R is nothing but 2.5 kilo ohms. From this we will get it as V0 is equal to 4.98 volts, and the circuit shown in this figure which gives the output voltage as a unipolar output voltage, and if you observe this circuit, the fourth pin will be represented the output current of the IC1408 and the direction of the arrow mark will be represented the output current direction, and which is inverse in this case. That means IC1408 sinks the output current. Whenever the binary inputs are, that means all the 8 inputs are zeros, then the output current will be equal to 0. That means IC1408 sinks 0 current. Similarly, whenever the binary input values are, all the values will be equal to 1, then the output current will be equal to 1.998 milliamperes. That means it sinks 1.998 milliamperes current, and this current will be converted into voltage with the help of I to V converters. Now when the binary input voltage is equal to zeros, that means all the binary inputs applied to the IC1408 are zeros, then the current will be equal to 0. Then obviously we will get the output voltage V0 is equal to 0 volts. Similarly, when the binary input are all ones, then you will get the output current as 1.998 milliamperes, and we all know that V0 is equal to minus I0 into RF. Okay, here the direction of I0 is like this. Whenever you are consider the I0 is like this, then the polarity will be changes. So minus of, what about I0? I0 is 1.998, but if you are considering the current passing through this op-amp feedback resistance is I0, then the current will be taken as minus 1.998 into 2.5, which is nothing but 4.988 volts. Okay, so by observing the output voltages of this equation, the IC1408, this typical circuit produces the unipolar output voltages, and with a slight modification to this circuit, we can produce the output as a bipolar output voltages. How can you modify the circuit? Is simply by adding a resistor R, which will be equal to 5 kilo ohms, connected in between the reference voltage to the output current terminal of the IC1408, then it produces a constant reference current as 1 milliampere. By changing the circuit like this, then you can produce the output as a bipolar output voltages. Now we are taken the modified IC1408, that is just we are adding the resistance RB in between the reference voltage to the output terminal of IC1408, then it produces the constant reference current. Okay, now the condition 1, when the binary input values are 0, so whenever we are applying the binary inputs are zeros, then we all know that the output current is calculated by using the formula I0 will be equal to V reference divided by R14 into A1 divided by 2 to the power of 1 plus so on plus A8 divided by 2 to the power of 8. So if you substitute the values, binary input values in this expression, then you will get the output current I0 will be equal to 0. Now what we are going to do is apply KCL at node A. Now what happened? That means the current entering at that node will be equal to the current leaving at that node. So here what happened is IB will be equal to I0 plus IF. So IB will be equal to I0 plus IF. So we can rewrite it as minus IB plus I naught plus IF will be equal to 0, and we all know that I naught will be equal to 0 milliamperes plus what about IB? From this circuit we calculated the reference current will be taken as minus 1 milliampere. How can you calculate? Is V reference is 5 volts divided by RB is equal to 5 kilo ohms, then we will get it as minus 1 milliampere plus IF is equal to 0. From this IF is equal to 1 milliampere. So V naught is equal to minus IF into RF. So we will get it as IF is minus 1 milliampere into RF is equal to 2.5 kilo ohms. So we will get it as minus 2.5. Okay, so we will get it as output voltage is equal to minus 2.5 kilo ohms. Similarly, the condition 2. Condition 2 is when the binary input voltage is 80H, then what happened? Then we calculated the output I naught is equal to V reference divided by R14 into N. 80H means 4 ones and 4 zeros. Okay, so A1 divided by 2 power 1 plus so on plus A8 divided by 2 power 8. And if you substitute those values and calculated the I naught value, you will get the I naught value will be equal to I naught will be equal to 1 milliampere. So once again applying the KCL at node A, then we will get it as minus IB plus I naught plus IF is equal to 0. Minus IB means the constant bias current, which is nothing but minus 1 milliampere plus 1 milliampere plus IF. So you will get it as IF is equal to 0. And we all know that V naught will be equal to minus of IF into RF. So we will get the output voltage as 0 volts when the input voltage is 80H. Similarly, we can calculate for the condition 3. What about for the condition 3? Whenever the input voltage, 80H means 1,000, 1,000 and 4 zeros H. Okay, not 4 ones, 4 zeros. 80H means 1,000, 4 zeros H. Then we will get the output current as 1 milliampere. Coming to the condition 3, when the binary input has taken as all the ones, then you will get the output current I naught. Just now we calculated it as 1.998 milliamperes. That we are going to consider here it as approximately equal to 2 milliamperes. Once again apply KCL at node A. So we will get it as minus IB plus I naught plus IF will be equal to 0. So minus 1 milliampere plus 2 milliamperes plus IF will be equal to 0. From this IF is equal to minus 1 milliampere. So output voltage V naught is equal to minus IF into RF. So minus 1 into RF is nothing but 2.5 kilo ohms. Okay, here it is minus 1 milliampere. So we will get it as minus of minus. So what we will get? Plus 2.5 volts. Okay, that's it for the condition 3. So if you compare the condition 1 with the condition 3, here we are getting the output voltage as plus 2.5 volts, and here you are getting the output voltage as minus 2.5 volts. That means what we can conclude from this IC 1408 is we can produce the bipolar output voltages with a slight modification for the IC 1408. The modification is nothing but we are going to insert a resistance RB whose whose value is 5 kilo ohms in between the reference voltage and the output terminal of the IC1408, and which produces the constant bias current, which is nothing but IB in this case. That will be taken as V reference divided by RB, where V reference is equal to plus 5 volts and RB will be equal to 5 kilo ohms. Then we will get it as 1 milliampere current, that is constant irrespective of the input voltages. The IC1408 DAC is an 8-bit R/2R ladder type DAC technique. Flash type ADC converters. When the system design calls for the high speed availability, then the flash type ADC converters are right choice for that, and they get their name because of the ability to do the conversion very rapidly. Flash type ADC converters are also called as simultaneous converters or parallel comparator converters, and because of the high speed conversion accomplished by providing 2 power n-1 number of comparators are required, and in these comparators the input is applied to one of the input terminal. Here I am going to take it as V in, which will be applied as one of the input terminal of the comparator, and the other input is nothing but the reference input. The InQ reference voltage will be applied to the reference input voltage of the comparator with 1 LSB apart. Okay, now this figure represents the 3-bit flash type A to D converter. In this 3-bit flash A to D converters, it requires 2 power n-1 number of comparators. So 2 to the power of 3 minus 1, which will be equal to 7. So for the 3-bit flash type A to D converter, we require 7 comparators, and one of the input is applied from the input terminal of the input terminal, and the other input is derived from the reference voltage derived network. This is nothing but the reference voltage divider network. From this reference voltage divider network, we are applying the reference voltage to the one of the input terminal of the comparator, which is nothing but the reference voltage, and in this case we are considering plus V reference will be taken as the full scale input voltage. So for that full scale input voltage, we are considering the V reference value, and the comparator produces the output as 1 or 0 depending upon the comparison with the reference voltage to the input voltage. So the input voltage is applied to the non-inverting input terminal of the comparator, and the reference voltage is applied to the inverting input terminal of the comparator. Whenever the comparison is happened between the input voltage to the reference voltage, if the input voltage is greater than the reference voltage, then the output is generated by the comparator is 1. Whenever the reference voltage is greater than the input voltage, then the output voltage produced by the comparator is equal to 0 in this case. So here you have to remember the non-inverting terminal is nothing but the input voltage which we are applied to all the input terminals of the comparator, and the inverting input terminals is nothing but the reference voltage. So according to the comparison, we are going to get the output as ones and zeros, and the comparator output codes are converted into the binary values by using the translator or encoder. In this case, we are going to be using it as a encoder. So what I am going to conclude is the output code of the comparator is converted into the digital data with the help of encoder, and we all know that the quantization error will be equal to plus or minus half LSB. Thus, for the ADC, the maximum input signal frequency, sine wave frequency input voltage is digitized accurately by plus or minus half LSB. So, the maximum frequency, input frequency is calculated as 1 by 2 pi into Tc into 2 to the power of n, where Tc is nothing but the conversion time and n is represents the number of bits and Fm is nothing but the maximum input frequency. The main advantage of this flash type A to D converter is the conversion time is very low. Another A to D converter is counter type ADC. The principle involved in the counter type ADC is the output of the DAC is continuously compared with the analog input value which is applied as an input of the ADC, and once the DAC output is greater than this analog input value, then we will be note down the input voltage of DAC, which is nothing but the binary output values of the equivalent analog input voltage which we are applied at the input of the ADC technique. That's the principle regarding to the counter type ADC. Now I am going to explain the operation of counter type ADC. This counter type ADC technique uses DAC for the conversion of A to D converter, and the output of the DAC is continuously comparing with the analog input voltage which we are up the A to D converter, and whenever the VD voltage is greater than the analog input voltage, then the output of the comparator is low, which stops or which disables the clock, and which binary counter stops counting the clock pulses, and we are going to consider the output of the binary counter as a equivalent digital output of the analog input value. And coming to the first case, first whenever we are going to start the operation of counter type ADC, initially we are going to reset the binary counter to 0, and the output of the binary counter is 0 whenever we are applying the reset pulse to the binary counter, and the output of the binary counter will be applied as an input of the DAC. So obviously the output of the DAC will be equal to 0, and the analog input voltage VA is greater than this VD value, and the analog input voltage VA is the voltage at the non-inverting input terminal of the comparator, and the VD voltage is the nothing but the voltage at the inverting input terminal of the comparator. Whenever the VD value is less than this value, then the comparator output is 1 and it activates the AND gate, and the clock is applied to the binary counter, then it starts counting the clock pulses. Whenever the value of the clock pulses is increases, then the output of the binary counter is increases. Whenever the binary counter output is increases, then obviously the DAC output is also increases. Whenever the VD value is greater than this analog input value, then what happened? The output voltage of the comparator goes low, which is nothing but here we are considering it as 0, which disables the AND gate and which stops passing of the clock signals to the binary counter, and the corresponding output of the binary counter is taken as the digital equivalent value for the applied analog input voltage. Whenever you want to perform for the other operation, then what you want to do is remove the analog input voltage and apply a new voltage, and before starting the experiment first the binary counter is reset to 0 volts. Okay, and the process is continued until the VD value will be greater than the analog input value. That's it for the counter type ADC tech. We are going to discuss about one of the type of A to D converter. Here the dual slope A to D converter is an indirect type of A to D converter. So here the dual slope A to D converter converts the analog input voltage Vi and negative reference voltage into time slots, and then it is measured by the binary counter. The process is a slow process. That means the conversion of analog signal into a digital signal is a slow process, but it is a accurate value. So coming to the circuit diagram of dual slope A to D converter, it consists of an integrator, comparator and binary counter, output latch, flip-flop and minus V reference. Now see the operation of the dual slope A to D converter. The ramp generator input is swings in between input voltage, analog input voltage Vi and minus V reference, and the analog switch S is controlled by using the MSB bit of binary counter. Whenever the MSB bit will be equal to 0, then the analog switch will be connected to the analog input voltage Vi. Whenever the MSB bit will be equal to 1, then the analog switch S will be connected to minus V reference value. Okay, now initially we are considering, that is at a time t is equal to 0, the analog switch S will be connected to analog input voltage. So the switch will be connected to analog input voltage. The integration of analog input voltage Vi starts integrate, and the output voltage of the integrator will be taken as, here V0 I is equal to minus 1 by R1 into C1 integral of 0 to T1 into Vi into dt, where R1 and C1 is the integration time constant and Vi is taken as a constant throughout the integration time period. So finally we will get the output voltage of an integrator is V0 I will be equal to minus of Vi into T1 divided by R1 into C1 at the end of 2 power n clock periods. Immediately the MSB of the counter will be changed from 0 to 1. Once the MSB bit is changed to 0 to 1, it results the flip-flop will be set to 1. Once the flip-flop output is set to 1, then it connects the analog switch S to the reference voltage, which is nothing but the negative reference voltage. Once the switch will be connected to the negative reference voltage, then the integrator produces the positive ramp signal. Why? Because here we are applying the input at the inverting input terminal of an integrator. So minus of minus will be nothing but plus. That's why I am telling you the positive ramp signal will be generated. And once the output of the integrator reaches to 0, immediately it disables the AND gate. Once it disables the AND gate, then it stops the number of clock pulses reaching to the binary counter. Counter will be stopped at the count where the number of clock pulses in time period T2. Okay, now in the time period T2, that is from this to this, in this time period, the V0 I will be taken as minus 1 by R1 C1 into integral of 0 to T2 minus of V reference into dt, which is nothing but V reference into R2 divided by T2 divided by R1 into C1. The integrator output voltage V, which is ramp to the V volts from 0 to V and back to the 0 volts, and where the charging voltage will be equal to the discharging voltage. So we will be consider that Vi into T1 divided by R1 C1 will be equal to V reference into T2 divided by R1 into C1, where R1 into C1 will be gets cancelled. Then you will get it as T2 will be equal to Vi into T1 divided by V reference. That means the time period T2, the actual integration will takes place in the time period T2. T2 will be directly proportional to input voltage Vi. Keep T1 and V reference is kept constant. So the actual integration of the input will be takes place during the time period T2. In the control circuit, we can connect the clock to the binary counter at the starting of T2, and we will be disconnect the clock from the binary counter at the end of time period T2. So the output of the binary counter is nothing but the output voltage of the digital output value of the analog input voltage, and the digital output will be calculated as counts per second into T2, which is nothing but counts per second into T2 is nothing but Vi into T1 divided by V reference. Once again, here I am writing that one. Digital output will be equal to counts per second into T2, and substitute the value of T2 in this place, then we will get it as counts per second into Vi into T1 divided by V reference. So the exact digital output of the applied analog input voltage will be getting in this case. One disadvantage for the dual slope ADC technique is it is a slow process, and the advantages are high accurate value and low cost, and the temperature variations on R1 and C1 will be very less in this dual slope ADC technique. Why I am calling it as an indirect method is here we are not directly comparing the input value with the reference value. Here we are comparing the output of the integrator with the reference value. So that's why we are calling it as an indirect method of A to D converter.